Recall that whenever an object is undergoing translational motion under constant linear acceleration, we can derive 4 kinematics equations that allow us to calculate a certain unknown variable knowing the other quantities. So here we have a list of the 4 kinematics equations for translational motion under constant linear acceleration. Now, in a very analogous way, we can also derive 4 kinematics equations for angular or rotational motion under constant angular acceleration. So, if the angular acceleration is constant, that means the average angular acceleration is equal to the instantaneous angular acceleration. And that means we can obtain the following 4 kinematics equations for angular motion. Now notice all we had to do from going from this side, from these equations, to these equations was simply to replace our translational physical quantities with the angular physical quantities. So we replaced the final and initial linear velocity with the final and initial angular velocity. We replaced the linear acceleration with the angular acceleration, and we replaced the final position and initial position with the final angle and the initial angle. So we can basically use these 4 angular motion kinematics equations to help us solve various types of problems involving angular or rotational motion. So let's look at the following example. Let's suppose that a centrifuge is accelerated from rest to a frequency of 25,000 revolutions per minute in an interval of 25 seconds. So using this information and these equations, we want to calculate part A and part B. In part A, we want to find the average angular acceleration, which is the same exact thing as the instantaneous angular acceleration because we have constant angular acceleration. And in part B, we want to find the number of revolutions made by the centrifuge during the time interval of 25 seconds, assuming we have constant angular acceleration. So let's begin with part A. Now, we basically want to use the frequency to calculate the angular velocity, and then we use the angular velocity to calculate the angular acceleration. But before we use the frequency, we have to convert the frequency from revolutions per minute to revolutions per second. So that basically means we take our quantity of 25,000 revolutions per minute and we multiply it by 1 minute divided by 60 seconds. So the minutes cancel and we're left with approximately 417 revolutions per second is our frequency. And now we can use this frequency and our relationship, our formula, to calculate the angular velocity. So recall that angular velocity is equal to 2 pi times frequency, where frequency is given in revolutions per second. So we take this quantity, plug it into this, multiplied by 2 pi, and we get approximately 2,618 radians per second is the angular frequency. And now recall, by definition, the average angular acceleration is equal to the change in our angular velocity divided by change in time. Now our initial angular velocity is 0. So that means we simply plug in this entire quantity into the top and the bottom becomes 25 seconds. So we divide 2618 by 25 and we get approximately 104.7 radians per second squared is our average angular acceleration, which is identical to the instantaneous angular acceleration. Now we go to part B. So now we want to calculate the number of revolutions made by the centrifuge during our time period. So to calculate that, we must first find the final angle measure in radians. So we have to use this first equation. Notice our initial angle measure is 0. So that means this entire value goes to 0 and we're left with this value. So now we know what our angular velocity is. We found it to be 2,618. We know what the time is. It's 25 seconds. And we just found what our average angular acceleration is. It's 104.7. So we use these quantities, plug it into our calculator and solve, and we get approximately 98,000 radians. So now we take this quantity and we recall that in one full revolution there are 2 pi radians. So that means if we want to find how many revolutions are in 98,000 radians, we simply take 98,000 and divide that by 2 pi. And we get approximately 16,000 revolutions. So that means in a time interval of 25 seconds, our object rotates 16,000 times.